as we look at our section in 7.2 and we keep doing with our sampling proportions or our sampling distributions, today we're going to focus in on proportions, which means we're dealing with categorical data. When we deal with means, we're dealing with quantitative data. That's going to be the next lesson in 7.3. That's pretty much the same as we keep going through. When we look at some of the other topics we're going to start studying in chapters 8, 9, 10, and 11, and so forth, when we're dealing with proportions, it's more categorical data that we're dealing with. Whereas when we're dealing with quantitative data, that means we're dealing with the means and that kind of stuff as we do things, as we prepare to run these different confidence intervals and hypothesis testing stuff. So basically, as we look at this one, how good of a statistic is p hat as an estimate for the parameter p? The sampling distribution of p hat answers the following question. Consider the appropriate sampling distribution generated by a simulation with simple random samples of Reese's Pieces or drawn from a population to proportion of orange candies is 45%. So we had this a couple scenarios here, and we were going to just analyze kind of the shape and the spread. What do we notice as things change? And again, we can use that little up in the top, that little applet up there to actually do this activity live if you want to sometime. So on the left-hand side here, they said, okay, maybe they say 45% of the Reese's Pieces candies are orange. And so eventually we get to test that claim as we do stuff later on. But if we were just trying to do a random sample and create a sampling distribution from it, they said on this first one here, our sample size is 25. So they just took 25 at a time. And they did 400 samples, so each one of those little dots represents a sample. In the middle here, they indicate where the mean is of 45% is what they're saying. Now, after they did all this data here, after they got all this data, first off, what can we say about the shape? It looks approximately what? Yeah, it looks approximately normal. It's approximately symmetric. Okay, it's approximately symmetric. It looks approximately normal. It has a feel of a bell-shaped curve. It's not too bad, so we would say it's approximately normal. And then, we noticed here is where here is where the mean is, the proportion population P is, right at about 4.5. And off of all those samples, the P hat ended up being 0.48 is what it ended up being. And so, they tell us what the standard deviation is. On the next side here, what they did was all they changed was, let's get a bigger N. Let's change N from 25 to 50. So they doubled it, and they created the sampling distribution. Then they said, okay, now what is the mean of that sampling distribution? What's the standard deviation? And if we notice on this one, as we just increased the sample size from 25 to 50, we got a better symmetrical curve here. Okay, this is more symmetrical, which we would say is pretty much normal. And it ties into what we were talking about last week about if we increase the sample size for each sample, we should get a more symmetrical appearance to what we're dealing with, which allows us to do the normal curve and allows us to do the normal CDF feature for calculating probabilities. Notice how the p hat, the p hat went to 0.46, which is a lot closer to what they said the population was by doing a bigger sample size. So when we look at shape, in some cases, the sampling distribution of P can be approximated by a normal curve. This seems to depend on both N, the size of the sample, and the proportion of the population P. The mean of the distribution of mu sub P hat is equal to P, the population proportion. Again, this makes sense because the sample proportion P hat is an unbiased estimator of the population proportion P. When we look at the spread for a specific value of P, the standard deviation of P hat gets smaller as N gets larger. We see that in the case of these Reese's Pieces. As N went from 25 to N equals 50, we went from a standard deviation of 0.103 to 0.068. So as we increased the sample size, we actually made the standard deviation got smaller. And therefore, we got more, our curve got better. It got to be more of a normal curve. So as we analyze just a generic little normal curve, there's a formula for the standard deviation. Again, we get to add another formula here. So to calculate the standard deviation, we would do P, the population proportion, times 1 minus P, and then over N. And there should be a little P hat here. Unfortunately, I copied and pasted this picture, so it didn't let me put a nice little P hat in there originally, like some of the other stuff I was able to type it in. But there should be a little P hat there. On the first part, we set up above the mean. The mean of P hat is equal to whatever the population proportion is what we can go ahead and set. Again, these are all the fundamental pieces we need to know in order to do like the normal CDF feature in the calculator to calculate the probabilities. Now, here's the key. Here's one thing. We can only calculate that standard deviation of P hat if we meet 10% condition. Remember, we use the 10% condition for the independence part. So we need to check to see, do we meet that independence condition? If we do, then let's calculate what the new standard deviation is. If we don't meet it, there's no point to calculate it, okay? Because that's not going to help us if we fail the independence part. So again, if you forgot what the 10% condition was, is that capital N has to be greater than or equal to 10 times little n. So basically 10 times our sample size has to be smaller than the population. It could be equal to, but the majority of the time we're going to be smaller. Okay. So if 10 times the sample size is bigger than the population, then we got an issue. Like, for example, if we did a random sample of 500 students at Beach High School, and then we're saying, okay, do we meet the 10% condition? Well, what's 10 times 500? 5,000, right? Are there 5,000 kids in the school? No, so we would fail the independence clause on that one, so we wouldn't go through and recalculate a standard deviation and do a normal, and try to do the normal probability stuff. Ideally, since we have 1,450 students roughly in our school, the max sample size we would want to do is maybe somewhere around 120. 140, you're cutting it close because 140 times 10 is 1,400. So if you're trying to gather data and you're trying to do stuff, the max you would want to do for our school is about 140 in a sample size, and do multiple things of 140, 140, 140. You wouldn't want to go above that because then we got a chance of failing that 10% condition. Because typically when you're doing people for a survey, you don't have replacement. So that's why we're checking that independence condition. As N increases, the sampling distribution of P becomes approximately normal. Therefore, we can do a normal condition. So we can do that normal CDF. And again, that also means that, hey, we got to check our conditions. So last week we learned that we would do N times P, is it greater than or equal to 10? And then is N times 1 minus P greater than or equal to 10? And if we are okay on both of those, then we meet the normal condition. Therefore, we can go ahead and do our normal CDF and calculate the probability of a certain thing taking place. And so that's what we get to do in this next page. As we finish up this little lesson here, is we get to run through those. And I get to introduce another thing in this lesson here. Well, what happens when we have two proportions, comparing two populations. But we'll do this one first here. About 75% of young adult internet users age 18 to 29 watch online videos. Suppose that a sample survey contacts a simple random sample of 1,000 young adult internet users and calculates the proportion p hat in this sample who watch online videos. What is the mean of the sampling distribution of p hat? We know from up above that the mean of p hat is equal to p. So what is our population proportion? 75%, so 0.75. Again, if you want to make a little note here, the mean of p hat is equal to population proportion p. They asked us to find the standard deviation. All right, well, we need to check the 10% condition to see if that's met. So with that in mind, there our sample n is equal to 1,000. 10 times 1,000 is 10,000. I would say it's reasonable to assume more than 10,000 18 to 29-year-old internet users. Okay. So obviously there's probably a lot more than that. But hey, we're definitely below the 10%. So now I can figure out the standard deviation. So the standard deviation of p hat is going to be equal to the square root, again, generically, p times 1 minus p over n inside the square root. So it's the square root of 0.75 times 0.25 over 1,000. Now we get to break that to the calculator. And in the calculator, that comes out to be 0.0139. So that's our standard deviation of p hat, 0.0139. Sorry, it's right in the middle of that correct there. Part C, it says, is the sampling distribution of p hat approximately normal? So now we're trying to check for normality. So can we do in step D, or in another step, could we do the normal CDF features? So is n times p greater than or equal to 10? So is 1,000 times 0.75 greater than or equal to 10? So that's 750. That's greater than or equal to 10. Then we also have to check, is n times 1 minus p. Remember, we just can't assume, since one is, the other one is. We have to show the work. Again, if you don't show the work like this, they don't have to give you credit when you say, yes, we meet the approximately normal condition. This is very minute amount of work, so we need to make sure we do it. Okay, we show all work. So in both cases, we met it. So normal condition is met. So this means that if they ask me a question of saying what's the probability that somewhere between this much and this much internet usage is happening, or greater than this amount or less than that amount, we can go ahead and use that normal CDF feature. Part D says if the sample size were 9,000, so instead of being 1,000, we're like n is equal to 9,000. How would this change the sampling distribution of p hat? Well, first off, are we still independent? Do we still have independence? 10 times 9,000 is 90,000. Reasonable to assume more than 90,000 internet users from the age of whatever to whatever? Yeah, I think so. All right, so it's reasonable to assume more than that. what was it, 18 to 29. 18 to 29. And again, you would want to make sure you use that in a nice sentence. Tack on the age there that we're talking about, not just in general internet users. And then now they don't ask us to calculate it. They just say, how would it change it? So based on earlier, as sample size increases, what happens to the standard deviation? As n increases, the standard deviation decreases. Again, they didn't ask us for it, but again, I would check the independence. Do we still meet it? Yes. Hey, as n gets bigger, we know the standard deviation gets smaller. The reason why is because inside of the fraction, we're dividing by a bigger number before we take the square root. So when we take the top and divide it by a bigger number, it's going to be a smaller number that gets square rooted. Therefore, it's going to be a smaller standard deviation compared to the original one. Our nice little four-step process is going to come into our play here in this chapter and beyond. The test, AP test, typically doesn't mention about using the four-step process. Our book does. The homework problems do. I usually try to put it on the test as well, just to kind of get you conditioned to doing the four steps, especially from these chapters on. But typically on the AP exam on a free response, they don't tell you to use a four-step process. But using that four-step process is a good model to kind of have it all laid out by, so you don't leave out something. So a polling organization asked the simple random sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students actually attend college within 50 miles of home. What is the probability that the random sample of 1,500 students will give a result within 2 percentage points of the true value? So, for the solution, first in the state phase, again, state, plan, do, conclude. Those are the four steps. In the state phase, we would want to specify what are we doing. We want to find the probability that the sample proportion falls between 0.33 and 0.37. How did they get that? The P was 0.35. And then they said within 2 percentage points. So they added 0.02 to get the 0.37. And then they subtracted the 0.02, and that gave us the 0.33. That's how they came up with those two numbers there. So we're going to let them know. Now, you could phrase it as saying, we want to find the probability that sample proportion falls within 2 percentage points of 35%. If you wanted to do that and not actually find those two numbers, but we're going to use those two numbers when we do the normal CDF if we get to that stage, if we meet those conditions, okay? Our plan phase, we would say something. We have a simple random sample. They told us there is a simple random sample of 1,500 drawn from a population which the proportion is, or P hat is 35%, attend college within 50 miles. Now, we check our independence. They tell us, the condition is met. There is more than 15,000 first-year college students. So they went off real quickly and said 10 times 1,500 is 15,000. All right, so some of your major big universities have at least 15,000 first-year college students at the university, just in that university alone, not just in general for the whole college system. The distribution is approximately normal. They showed that n times p hat is equal to 525, which is greater than or equal to 10, and n times 1 minus p hat was 975, which is greater than or equal to 10. Again, real easy work to show to support what we're doing. If you don't show that stage saying, you say, yeah, it's approximately normal. They don't have to give you credit for that part of the phase. So in the do stage, we get to, before we get started, we know we want to find out what is the probability that P hat is between 0.33 and 0.37. That's what we want to find out. We know we can use the normal CDF since the normal condition is met. My lower bound, 0.33. My upper bound, 0.37. My mean is 0.35. Now here's where we got to be careful. My standard deviation. This is now we need to do the formula. The standard deviation for p hat in this case would be the square root of 0.35 times 1 minus 0.35 over 1,500. So what is 0.35 times 0.65 over 1,500? And then square root it. Remember, we want to use as many decimals as we can. I think the first 5 decimals are like this, 0.89562. Now, I'll be honest with you. I like trying to put in the formula and let it do the math for me, so I don't have to do this twice. I like putting in, for the standard deviation, square root, and then I would do parentheses, and I would do 0.35 times 0.65 divided by, and then 1,500. All right, I'm going to do that on my screen here in a second, but I like doing it that way. That way it takes all the decimals and it puts it in there for me. You can also use the variables button and do statistics too as well if you want. So I'm going to split my screen, get to a calculator. Come on, calculator. There we go. So with this in mind, second vars, normal CDF, 0.33, 0.37, 0.35. And then now for the standard deviation, I'm going to do second x squared. This is where I'm going to do parentheses 0.35 times 0.65. Close the parentheses just to say I'm closing the numerator. And then divided by 1,500. And then I'm closing the whole square root. That's how I typed it in there. The first parentheses just say, hey, we're taking the square root of the next stuff. I like separating it so that the calculator knows these two numbers multiplied together is my numerator, then the division sign, and then the denominator, and then I close off the parentheses to let it know that there's nothing else being put in there. So that's how I like keying it in there. And then we go down to paste, hit enter twice, and then there's our decimal that we have there. Notice they give us the rest of it. 3, 3, 3, 2, 4. Again, all we, now that's my probability. Sorry, that's not the, that's actually the percentage, sorry. Very similar to, yeah, that's right. I did that to the probability. The probability, that's our overall probability. Let me rewrite this. That's our answer. 0.8956 is our probability. The standard deviation individually, sorry, my bad. The standard deviation individually was like 0.0123153021. Okay, that's what that standard deviation worked out to be. I decided to bypass that stage instead of having to type all that numbers in. I went through and did it separate. Now you can use your variables if you want to, or use the answer. Like if you wanted to take the time and type in your calculator second x squared, then give me a fraction, 0.35 times 0.65 divided by 1,500, and got enter. Now you could do your normal CDF, and then for the standard deviation, we could go down here and just say second negative sign, saying the last answer I just calculated, let it be my standard deviation. And when I hit enter a couple times, you'll notice it's the same answer. Okay, so there are a couple different ways you do it. Again, on a time-sensitive test, I like typing in the formula and letting it do the math and keep all the decimal places. So, anyway, next one. So we would say about 0.56% of the simple random samples of size 1,500 would give us a result within 2 percentage points. I'm trying to get rid of that calculator. 2 percentage points of the population. And there's a nice little short, quick explanation as we do this. And again, as we get further, we'll learn some scripting that we get to say for some of the situations. Now, before we finish up this lesson, sometimes we have a difference in proportions where they want to find is there a difference between the two. So here they say, when this is just generic notes, choose a simple random sample of size n sub 1 from population 1 with a proportion of success as P1 they label, and a separate independent simple random sample from a different population of size n sub 2, which means they don't have to have the same ends. It'd be great if they did the same sample size, but maybe based on what populations where they went with one being a group of 40 and the other one were a group of 30, okay? So if we were trying to figure out the probability that the difference between the two things would be a certain way, we would actually have to go through this kind of little process here. The sampling distribution for P hat 1 minus P hat 2 is approximately normal if the large count condition is met for both samples. So we get to use the normal CDF feature if we meet the normal condition for both, and we have to show all that math. Okay, that's a lot of math to show, but we have to do it. How do we come up with the mean? Well, the mean of our P1 hat minus P2 hat is just subtracting the two original population proportions. How do we get the standard deviation? We would take each of them individually, add them together inside of its fractions, add them together, and then square root it. And again, we can do that as long as both samples meet the 10% condition. I have an example for us to run through here in a minute of doing this process, okay? So note that the formula for the standard deviation is exactly correct only when we have two types of independence. Independent samples, so that we can add the variances. Remember, we never just add standard deviations, we have to add the variances. And then independent observations within each sample. When sampling without replacement, the actual value of the standard deviation is smaller than the formula suggests. However, if the 10% condition is met, the difference is negligible. The standard deviation of the sampling distribution tells us how much difference in sample proportions will typically vary from the difference in population proportions if we repeat this many, many, many times. Okay? So that's what it tells us. All right, so let's do an example. You got goldfish. Your teacher brings 2 bags of colored goldfish crackers to class. Bag 1. So I'm going to write some stuff down here. Bag 1 has a P hat of 25%. Red crackers, and this is, we're doing red. So red. And then in bag 2, it has a P hat of 35%. So P hat is equal to 0.25. The P hat is equal to 0.35. Each bag contains more than 1,000 crackers. Using a paper cup, your teacher just takes a simple random sample of 50 crackers from bag 1 and an independent simple random sample of 40 crackers from bag 2. Let P1 minus P2, so bag 1 minus bag 2, be the difference in the sample proportions. What is the shape of the sampling distribution and why? All right, so let's walk through it. The shape, 1, did they give us a graph? They don't give us a dot plot, do they? Okay, so this is where we get to say, all right, is it approximately normal? Is it approximately normal? So let's check. Is, for bag 1, is, they said N was 50. So N was 50. And our P for bag 1, or P hat for bag 1 was 25%. So is 50 times 0.25 greater than or equal to 10? That would be what? Is that 12.5? Right? Yeah. All right. And then if I do 50 times 0.75. That gives us what? 38.5 or 37.5? 37.5. All right, so we look normal for bag 1. I also have to check bag 2. I also have to do this for bag 2. So for bag 2, we would say, again, the N was 40, and the P hat was 35. So 40 times 0.35, are you greater than or equal to 10? What's that? Is that 14? And then on the other one is 40 times 0.65, greater than or equal to 10. And that would give us 26. All right, so we can say it is approximately normal. Because normal condition met. For both bags. All right, so we can say the shape is approximately normal. Anytime we're doing the difference between two things, that's the longer types of these problems. We have a bunch of those throughout the course. Part B, it says find the mean of the sampling distribution. So what is the mean of P1 hat minus P2 hat? Well, we learned all we had to do is just subtract the 2. So what is in the order, if we're saying P1, if P1 hat is bag 1, then we would just say 0.25 minus 0.35, which is equal to a negative 0.10. It's okay to have a negative. When they tell you to find the difference between two things, pay attention to how they label it. Usually with the context, they'll say like bag 1 minus bag 2 or bag 2 minus bag 1. I've seen problems where they're doing the difference between males and females, and they'll say, hey, males minus females or something like that. So pay attention to how they phrase it, and that lets you know how to set up that part for the mean. Part C, they asked us to calculate and interpret the standard deviation. Verify the 10% conditions met. All right, so first, before we do the calculation, let's do the condition. 10% condition. So for bag 1, our N is equal to 50. 50 times 10 is equal to 500. That is less than the 1,000 that they said was in the bag. So we're good on that one. Then for bag 2, we had N was equal to 40. So 40 times 10 is 400. That is less than the 1,000 because they said both bags had 1,000 fishies. So we meet the condition there. So now we can go ahead and calculate the standard deviation. So the standard deviation of P1 hat minus P2 hat equals the square root. And remember, it's 2 fractions in there being added. So 0.25 times 0.75 over 50. And then it's 0.35 times 0.65 over 40. And then, again, we can let the calculator do a whole bunch of the work for us if we want. All right, the math works out to be 0.0971. That's what my standard deviation is. All right, part D. They ask us to estimate the probability that the portion of red crackers in bag 1, so P1 hat is greater than P2 hat. So technically we could bring the P2 hat over to the same side. And that tells us that we're doing P1 hat minus P2 hat. Is it greater than 0? Okay. So we're trying to find the probability that P1 hat minus P2 hat is greater than 0, which means that it's positive. Okay? So that's what we're trying to find. Again, all I did was, bring it over here. You just bring the P2 hat over to the same side. So normal CDF. And then now we got to figure out, okay, what is my lower bound? Yo.
Can you explain how you got the P1 hat minus P2 hat?
Well, the statement in the problem is said that P1 hat is greater than P2 hat. So that means that it's got to be a bigger number. So if I brought P2 hat over by just an operation, subtract it from both sides, we come up with the inequality that the difference between the two is positive. It's greater than 0. Okay? So now, here's my lower bound. I'm trying to see, is it positive? Is it greater than 0? So my lower bound is 0. My upper bound, some really big number. I'm going to go 10,000. I'm going to go 100,000 fishies. Technically, you could probably stop at 1,000 fishies, but I'm just going to go ahead and put a big number. Our mean in this case was negative 0.10. And then our standard deviation. We're going to use the decimal we have there, so we may all be off a smidge because I really don't want to type in that big fraction. I mean, it'd be great if I kept a bigger, longer decimal there. Did anybody have that decimal? Anybody do it by hand before I got to it? So remember, we want to use all those significant digits in this next part. Ideally, if you have time on the test, type in the whole fraction. 0.25 times 0.75 over 50 plus 0.35 times 0.65 over 40. Type that in there, okay? It'll take a while, and it's not going to be pretty, so it may be something you want to do separate on the screen and then insert that answer, okay? Because trying to type that with parentheses in the normal CDF feature, it's going to be really crazy. So I'd probably do that one separate on a clear screen. Use the square root button, use the fraction button twice, get that answer, and then when you do the normal CDF, when you got to the standard deviation, just do second negative sign to pull that answer in. Okay, that would just save you a lot of hassle. All right, so with that in mind, we get 0.1515 is what we get. So there's a 15.15. There's a 15.15% chance that P1 hat will be greater than P2 hat. Again, I would want to write a little bit better with this context of the problem, that there's a greater proportion of red crackers in bag 1 compared to the one in bag 2. We would want to use the context of the problem, but that's a quick little thing that we would do, okay? Those are the harder ones because they're just longer. You have to do both samples at the same time with it together, find the difference.